Today I would like to talk to you about the research that we've been doing on security analysis of state machines, so implementations of state machines to be specific, and we focus on black box analysis. And what we did exactly we'll come back to in a bit, but first I will try to give you a quick motivation and some very small introduction just to make sure that we're all on the same page. So let's start with why would we be interested in state machines in the first place. So almost every protocol will include some kind of state that we have to keep track of, and especially in security protocols, these states can be quite interesting. So some typical types of states that we might be interested in is did the user already authenticate or not? So maybe we only want to perform certain actions after authentication. Did we already agree on keys? Exactly which keys did we agree on? Did we already start encrypting all our traffic, or is it still fine to accept plain text data? So these are all kind of things that you need to keep track of while performing a protocol. And a state machine is a model that contains all the possible states of a protocol and how to transition between these different states. And we'll come back to an example in a bit. So every application that wants to implement a particular protocol also will have to implement the corresponding state machine. So typically this is done rather implicitly, and lots of stuff can go wrong there, as we will see in a bit. But basically what you have to do is, once you have an incoming message, you have to decide, based on your current state, what action to perform based on this message. So maybe you don't even expect this message, you can just safely ignore it. Maybe you have to perform some cryptographic calculations to derive session keys and so on. You have to determine which message to respond with. So do you send back an error message or just the next message in the protocol? And finally, you have to decide on what the next state is in the protocol that you're going to. And if you make mistakes in the implementation of the state machine, then this can have some very serious impact on your security, and we will see some examples of this later on. So this is a really simplified version of a state machine. So you can see that we have two states in here. So the top state is the initial state. You can there try to, for example, confirm a transaction. It will fail, and you stay in this initial state, so nothing happens. You can try to send, for example, a verify PIN command. Well, here you see that if you try PIN 4 times 0, then it will fail, so that's apparently the incorrect PIN code. If you try 1, 2, 3, 4, then you go to the next state, so you get an OK message back. And apparently this is the correct PIN code, and in the next state, so in the second state, that's apparently the authenticated state, we can actually perform some sensitive actions. So in this example, confirm a transaction. So this state machine is not complete. We're missing some outgoing arrows here. But just to give you a rough idea of how we can visualize these state machines. Now let's continue to implementations of state machines. So we have some developers, they try to implement some kind of protocol, so either TLS, EMV, or some other security protocol. How do we then know that the state machine is implemented correctly? So as I said before, often this state is somehow encoded quite implicitly. So it can, for example, be you check whether some kind of variable is not null anymore, so whether you already set a key or not. So it's not just one variable that tells you exactly what the current state is. Usually it's a combination of all kinds of different variables that together define your state. And once you start to do funny things, you can mess up the values of these variables, and then your implementation might get a bit confused about in which state it is exactly. So one way to test whether you implemented a state machine correctly is test whether your implementation works with other implementations, so whether it's compatible at least. But of course, this will typically only test the happy flow, so it will see if you are compatible, if you speak the same language as the implementation on the other side. But we have no clue how the implementation will behave if you start sending invalid sequences, so if you start sending messages in wrong orders, or you start dropping particular messages. So what can we do about this? So one direction that we've been looking at is trying to extract state machines from implementations in a black box way. And one way to do this is something called state machine inference. So state machine inference is a completely black box technique that you can use to extract state machines from implementations. And this is done only by communicating with the system, so we do not even need to have access to the system itself. We don't need access to the source code. We only need to be able to communicate with the other system. So with, for example, TLS, this is quite convenient. You just need a network connection to a server, for example, if we try to learn a state machine for this. And that's all we need to extract the state machine using this technique. So basically, what we will be doing is we fuzz the order of the messages. So we try all kinds of different orderings of messages, and then based on the responses from the server or the client, we try to build up a state machine. And as we will see later, this is quite a useful technique for security analysis, so you can use it to discover vulnerabilities and bugs in these state machine implementations. Sometimes it can also provide you some interesting insights in codes, or in code, so you can see how implementers interpreted specifications, and usually they do this all in a unique way. So the only downside of this technique is that you will not find very carefully hidden backdoors. So it's really to find a state machine that is implemented by at least a somewhat well-willing developer. But if there is, for example, a backdoor, if you send the same message 1,000 times, something weird happens, or if you send a very specific payload, then this technique is not going to help you. But nevertheless, we can have some very interesting results using just this technique. So I would like to continue by giving you a rough idea of how this state machine inference works. So it works based on hypothesis, and you start communicating with your system under test, and then based on the responses that you get, you try to extend your hypothesis until at some point you are satisfied and you think that you have learned a complete state machine by now. So you will start with just an empty hypothesis. We have no clue about this system that we're analyzing. We just have an initial state and we don't know anything else. So we start by sending just a single message to this system. So this is an example for example, TLS. So we send a client hello message to the system, and we see that the server responds with a server hello message. So we update our hypothesis. We add a self loop saying that if we send a client hello message, then the server will always respond with a server hello message, and we stay in the same state. Then we try another message. We see that all the other messages actually result in fatal alerts and closed connections. So we update our hypothesis, and we now have a hypothesis for all the possible messages for one particular state. And then we continue. We try to see what happens if we send combinations of two messages. And then we suddenly see that if we send client hello twice, then we suddenly get a fatal alert and the connection is closed again. So apparently our hypothesis so far was not correct yet. So we will have to update it. So we have to add another state, because apparently if you send a client hello message, you end up in a different state because the second time you send this message, you suddenly get something else back and not a server hello message anymore. So we add this second state to our hypothesis, where we have a self loop with the client hello in the second state and then expect a fatal alert back. And we continue this process until we have some hypothesis that we're relatively sure about that it's correct. Okay, so this happens if you do your presentation, it's not on your own system. So what we're trying to learn are actually deterministic Mealy machines. So for every state, for every input, you have a next state and you have a corresponding output. And the output can also be empty in particular cases. And on a very abstract level, you can see it as there are basically two components. There is a learner and there is a teacher. In theory, the teacher knows exactly what state machine you are looking for. But of course, in practice, this doesn't work like that, because if we had a system that already knows exactly what the state machine was, we wouldn't have to bother learning it anymore. But the learning component tries to actually infer the state machine that is implemented, and it can do this using three different types of actions or queries. So one that every implementation will need is you will need to have a reset query. So the reset query brings your target system back into its initial state. Because if we don't know in which state it currently is, then deducing the full state machine becomes a bit more tricky. So we want to have a reset to get it to its initial state. So for network servers, this is typically fairly easy. We just set up a new socket, and we assume that we didn't do anything major on the server side to crash it. Then the second type of action are so-called output queries, so the queries that we've seen before. You send a particular message to the implementation, and you see what you get back. And then by combining these reset queries and these output queries, the learner will try to build up a hypothesis, as we've seen before. And then once it's convinced that it has something useful, it will give this hypothesis to the teacher, and this is done using a so-called equivalence query. And the teacher then tells you, yes, you indeed found the correct state machine, or it can say, no, you did not find the correct state machine, and here's a counterexample. And if you get a counterexample, the learner will update its hypothesis, continue a bit more learning if necessary, and then once it's convinced again, it will perform another equivalence query. And these equivalence queries will need to be approximated, of course, because, as I said before, the teacher doesn't know exactly which state machine is implemented. So we have some algorithms to approximate this. So one easy way is to do this using random checking. So you just check, for example, 1,000 different queries of different lengths. And if they all match between the implementation and the model that you just learned, we assume that it's correct. If you want a bit more certainty, you can use algorithms like, for example, the W method by Chow, and then given an upper limit on the number of states, the algorithm will actually be able to determine whether it's correct or not. But of course, then you still need to be able to tell the upper limit on the number of states. And well, the higher you set it, the more expensive it becomes to actually verify this. So these algorithms work on abstract symbols, so-called input and output symbols. So input symbols are the messages or correspond with messages that go to your system under test. And the output symbols correspond with messages that you actually get back. So we need some kind of software to actually convert these abstract symbols to actually bytes that we can send to the other side. And we have some layer of abstraction there. So for example, we can leave out the sequence numbers, or as you've seen before, we can have an abstract symbol that says just client hello, and then leave it up to the lower level implementation to actually fill in some sensible values in there. So basically what you will need if you want to use this method is you need a stateless implementation of the protocol. because you will need to be able to send messages in all different orders. So you will not just go through the happy flow. You might also have to start with the last message. And if that last message happens to be an encrypted message, then you already have to make sure that at least you initialize the keys to some kind of sensible value. So here you can see how we did this for bank cards, for example. We have the learner who sends command types, so these are EMV commands. It sends it to the so-called test harness or mapper, and the mapper then converts it to actual smart card commands that the smart cards will understand and will interpret the returned responses. So the algorithms can also work with this. So we looked at different types of systems. So we looked at real-world systems. So we started off with a bank card. We looked at handheld readers for online banking. We looked at the TLS protocol, so we looked at a collection of various well-known or widely used TLS implementations. We found some interesting things over there. We looked at different OpenSSL versions from the last 14 years. And next I will go into a bit more detail of these use cases. And next to this, we also looked at different protocols. So for example, SSH, and we're also looking at some other VPN protocols at the moment as well. So the tool that we use for this is called State Learner. So it's available on GitHub, and it's actually built around a library that's developed at TU Dortmund called LearnLib. So this library provides us with all the learning algorithms. And State Learner provides a nice wrapper around this and has, for example, built-in support to test TLS implementations or smart card implementations, but it can also be fairly easily be extended to analyze other protocols. So let's start with the first use case. So we started off with bank cards, as I said before. So these bank cards typically use the EMV protocol. So EMV stands for EuroPay, MasterCard, and Visa. So these are the three companies that somewhere in the 90s started with this standard. And the standard is now maintained by a company called EMVCo, or an organization, and is owned by well, a whole list of credit card companies by now. So as your regular industrial standard, I guess, it's quite extensive, has lots of options. So the specifications are over 700 pages. So that's divided over 4 books. And this is just a contact standard. So if you want to look at the contactless standard, you get some 4 more books on top of that. Even if you have all of these specifications, you're still not there, because every payment provider has their own specifications built on top of this. So for example, MasterCard has their own specifications and configurations. But unfortunately, these are not public. So you have to guess a bit there what they did. And the standard, as I said before, offers you many options. So you have different ways of authenticating your card. So if you put it into a terminal, the terminal wants to know whether the card that you just inserted is genuine. There are different methods for that. There are different methods to authenticate the card holder. So typically this is done by you entering your PIN code, but even entering your PIN code, it can either be verified by the card directly or by the bank online. And then you also have different types of transactions. So you can have online transactions where the card starts communicating with the backend of your bank, or it can be offline, so there's no online connection necessary. And then all of these options can be parameterized using so-called data object lists. So there's quite some choices to be made, and also quite some things that could possibly go wrong. So what we did for this research, we went around to colleagues, asked them for their bank cards. We managed to convince about 16 to actually hand over some bank cards. So usually we got old bank cards. People didn't really like us playing with their bank cards that they still wanted to use for groceries in the afternoon, but we could still get some nice results from this. So these models contained 4 to 8 different states. So here you can already see that these are quite different. And typically it took us less than 20 minutes to construct a model or to learn a state machine from a single card. So actually we did find one of the MasterCard specifications somewhere online with a state machine in there. So they did have it in their specifications, but still the cards that we analyzed didn't follow this state machine exactly. So they did some things differently. So fortunately or unfortunately, we did not find any security problems in these bank cards. So that's why I'm still giving presentations in Bochum instead of sitting on the beach in the Bahamas. But still, we could see some interesting results in these models. I also tried to do the same on a contactless card, so the protocol is fairly similar. But so when learning this, you send lots of messages, you start lots of new transactions. All these contact cards were perfectly fine with this. The contactless card did not like it so much, so after a couple of thousands of failed transactions, it actually blocked. And then we couldn't get it back anymore, so we gave up on that direction now. So this is typically what you got out of this. I'm not expecting you to read what's there. So you have lots of transitions, so these are all kinds of different messages that are sent to the implementation. Then we clean it up a bit, we merge some transitions that give you the same output, make the output a bit more readable, then you get something that looks a bit more useful. And then if we get rid of a bit more, we can actually get models that you would be able to understand, given that you've read 700 pages of EMV spec. So this looks all more or less what you would expect. As I said, we've done this for many different cards. So here you see 2 models of both Maestro cards, so MasterCard cards, but one is actually from a Dutch bank, so the left one is from the Rabobank, the right one is from the Volksbank, a German bank, and you can see that even here, though they both implement Maestro, they both actually have a different state machine. And then, yeah, so we also looked at some EMV cap applications. So these are the applications that are used by your handheld readers if you do some online banking. So then you insert your card into one of these readers, you enter your PIN code, enter some random looking code from your bank, and you get a random looking code back that you enter again on the website. And here you can see, so somewhere at the bottom you see that there is a generate AC and for a TC, and you get a TC back. But in order to be able to do this, you will always have to go via this verify step. So this is the step where your PIN code is verified. So in this case, it's only possible to get those the correct digits to enter on your banking website if you actually entered the PIN code on your card before, and it was correct. So then we continued to another device. So we went on to some other banking applications. So there was this interesting device that was introduced. So this was called the Identifier 2. So this is used by a Dutch bank, the ABN AMRO bank. And it actually has support for a USB cable. So you can, with a USB cable, you can connect it to your PC. And then if you do an online transaction, it will display some meaningful information on the device. So how much money you are transferring to which bank account. So if you do this correctly, of course it's a very good idea, because if you just enter some random numbers on this device, you have no clue exactly which transaction you're authenticating. If you actually sign one of these messages that says, I'm not now going to transfer 1,000 euros to this and this account, then at least you know what's happening. So we thought it was a good idea that they would try this. So we had a master's student who was looking into this because we wanted to understand exactly how they were doing this. So originally we thought, well, maybe we can use it for something else as well. Later it turned out that we forgot about this plan and we didn't bother anymore because turned out it was not such a good idea after all. So in this analysis from this master's student, we found a serious security flaw, so we will come back to this later. Also, we found some other funny stuff, so there are some standard text that you can display on this device using JavaScript from your browser. So one of the messages is follow the instructions on your computer. So, well, if you display that and then refer the users back to your computer that we didn't trust, so we added another device, then it's maybe not the best idea ever. And you can also, with some effort, you can get your own text on there as well. So we found this through some manual analysis. So we looked at USB traffic, tried to figure out what kind of communication was going on between the smart card and the device. And next we wanted to know if we can actually automate this type of analysis, whether we can also find these kind of bugs using automated tools. But there was a bit of a problem because, well, this identifier, you actually have to enter your PIN code, you have an OK button, a cancel button. So it's not as easy as with the bank cards. We just send some data over a connection and then get some data back. Now we actually had to physically press some buttons to get anywhere interesting in the protocol. So we had two students from Austria visiting us, looking for a project. So what we did, we gave them a box of Lego to play with. And then in the end, we had a Lego robot that could actually push the buttons for us. So we had, there are 3 motors on this robot that can press different buttons. So obviously we want to have the OK button and the cancel button. But next to that, we also need to be able to enter the PIN code. So for this, we just added a motor to press one of the digits and programmed our own bank card, which basically mimics a real bank card, except that unfortunately it didn't work in the ATM. But it did accept all the PIN codes that you entered. So it was enough if we could just press one digit 4 times and then get a valid PIN code verification. Next to that, the Raspberry Pi also controlled the power USB line. So as I said before, we need to get the system under test back to its initial state. And the only way we managed to do that with this handheld reader, because we cannot just set up a new socket, that doesn't make any sense. We actually had to cut the power to the device to get it to reset, and then we could try another session. If you're interested to see how one of the early versions of this robot look like and functions, you can find the video online on YouTube, and I think you should also be able to find this link on my website. So during this project, we also found out that apparently these devices these buttons on these devices are not meant to be pressed thousands and thousands of times. So at some point, I got some non-deterministic behavior. And then after lots of debugging, I found out that actually once in a while the button got stuck because it just wore down by pressing it so many times. But luckily we still had 9 digits left, so we moved the motor a bit and then we could continue with the same reader again. So here you can see one of the earlier versions of the robot. So you can see the Raspberry Pi on the left corner and then the device on top. So you can see a bit of the identifier sticking out with the bank card. Of course, I also wanted to play a bit with Lego, so I improved the robot later on as well. So you can still see the Austrian and Dutch flag on top of there. So here you can see the identifier 2 in there with the USB connection that's going to the Raspberry Pi that's used to send the necessary USB commands. And here you see it from the other side, so that's our own bank card that we programmed that will accept any PIN code, but will not give you any money. So to just give you an idea how this protocol works with this device, so we have the host PC on the left, so that's where your browser is running and where you're trying to do your online transaction. And we have the USB reader in the middle, and we have a smart card that's inserted. So the first thing you will have to do is to actually enter your PIN code. This PIN code is then verified with the smart card. And if the PIN code was okay, then the host PC will send some transaction relevant data, like, for example, the amount to the device. And the device will then show this to you. So here you can see it's a transaction for 5,000 euros. And the user will then have to approve this by pressing OK. The reader then tells the host PC, OK, the user just pressed OK. And the host PC tells the reader, OK, that's great, now please generate the signature that we need to confirm this transaction. And then the last couple of messages are used to actually generate a MAC that will be used to confirm your transaction. But if we look at this part, this is a bit fishy. There is no reason why you would have to tell the PC to, yes, the user just pressed OK, and then the user, or then the PC telling the device, the user pressed OK, now generate the signature. So it can work like this if you implement it properly and you keep track of your current state. Unfortunately, that's not what happened. So if you leave out this message from the device, or you don't wait for the device to say the user pressed OK, now continue, you can also just immediately ask for the signature, and the device will also happily provide you with this signature. So if this happens, you will see the transaction details for a fraction of a second, and then immediately the screen goes blank again, and your transaction is approved. So we reported this obviously to the bank, and it's now fixed. So we also got hold of the new fixed device. So this actually gave us two different devices to test with. So we tried to learn the state machine for both of these devices. So on top you see the old device, and at the bottom you see the new improved firmware. And here this is actually a message that goes to a state in which you just sent an unconfirmed cryptogram, so you can actually send this message. You can actually get this signature without ever having to press the OK button. So here we combined a couple of messages, because we could have, for example, an input message that's enter just one PIN, but probably the only thing that you will learn is that you will actually have to enter 4 digits in a row, and it will just really slow down the analysis. And we combined some other messages that would make sense to be together. We also tried a bit more fine-grained number of input messages, and then we ended up with this very weird state machine with all kinds of states that you would actually not expect in there. But because of all these manual interactions, so the pushing of the buttons is not extremely fast. It takes quite a while for these big models to learn. And especially the first device was also somewhat slightly buggy and could react non-deterministically, which is a bit of a problem for the algorithm. And then the next protocol that we looked at was TLS. So we've already seen this protocol before today. So this is just a generic version. So you start with the client hello, then the server will respond with a couple of messages, hopefully including a server certificate. The client will respond with some key material that can be used for key establishment. And then after the change cipherspec message, once you receive this, all incoming communication should be encrypted. And then to finish the handshake, you have a finished message, and this finished message actually provides integrity over all the previous message in the handshake, both the ones you sent and the ones you received. And the other side will then also respond to the change cipherspec message to indicate that from now on all its data will be encrypted. And it will also send a finished message to provide integrity over all the previous messages. And then at the end, we can start exchanging application data safely. So to do this, we again needed an almost stateless TLS implementation. So you can find this in State Learner. You need a bit of minimal state to actually keep track of the keys that you just agreed on. Otherwise, you don't get anywhere in this protocol. We did some tests on both client and server implementations, and we supported all regular TLS messages, as well as the, well, by now famous heartbeat extension. So we also found some interesting things there. And we had support for different key exchange algorithms and some client authentication, and we needed some special symbols to indicate exceptions that happened in the test harness. So for example, if the MAC verification failed, then we want to know this because this is actually an interesting event that we might want to do something with. So we looked at a whole list of different TLS implementations. So we have the more well-known ones, OpenSSL and its forks, GNU TLS, Java's implementation, Embed, and some others, and also two more scientific implementations, so MeTLS by Microsoft Research and INRIA, and not quite so broken TLS from some people in Cambridge. And what we noticed was that actually every model that we learned was different. So not one or not, well, two implementations were the same. And even if you look within implementations, the state machine can change quite a lot over time. So when available, we used demo applications and also the number of states. There was a great variation in that, so it ranges from 6 states, which you could kind of expect with TLS, to up to 16 states, which is definitely way too much. Yeah, so I'll just, and we found some flaws in different implementations, so I will just quickly go there. So here you can see all kinds of different models. So these are all different implementations, and they all look different. So this was one of the more interesting things that we came across. So in the Java version, you could actually just skip the change cipherspec message. So recall that this change cipherspec message indicates that from now on, you're encrypting all your data. So if you skip this message, then after this, you can just start communicating, or at least sending data in plain text. So that's exactly what happened here. There you see the red transition. That's the one you would not expect in there. So the green one is just a happy flow. But if you send a finished message before ever sending a change cipherspec message, then the server will happily accept any plain text data that you send it that way. And for the client side, it was even worse. You can send a finished message even earlier, and then the client doesn't even bother anymore about certificates that you didn't send yet or encrypting, and then all data is in the clear. So this issue was actually found by the Prosecco group at INRIA at the same time, even though it must have been in there for years. Apparently, we were looking at this implementation simultaneously, so we only found this out once I was visiting them and presenting this work. So then for GNU TLS, we found some very weird behavior there. If you send a heartbeat message during the handshake, you suddenly end up in a sort of a shadow path where you can never get out again. So according to the specs, you should ignore heartbeat messages. So this is more or less what happened in GNU TLS, except that it also then forgot all of the previous messages. So typically all the messages are collected because you will need them in the computation for the finished message to provide integrity over all the previous messages. But in GNU TLS, it just emptied this buffer and forgot all about the previous messages. So then you could see that somewhere at the end, there was an internal error because the finished message that you sent to it suddenly didn't make any sense anymore. So later, we also did an analysis of 14 years of state machines, of OpenSSL and LibreSSL. So I looked at almost 150 versions of OpenSSL. So I didn't do this manually. I wrote some scripts to do this. And then I could actually see that for example, OpenSSL, there were 15 different state machines. And they reached between 17 states and 6 states. On the client side, it was also quite varied. So this is the earliest version that I looked at. It looks pretty horrible, and there are way too many states. So even if you clean it up, you have way more states than you would expect. So I'll just skip over the next point. So if you're interested in the vulnerabilities that you can find in this, you can have a look at the paper on my website. But so this was the latest version that I analyzed for this research. And then you can see that actually in the 14 years, things did improve quite a lot. And now we just have a very simple state machine, and this is more or less what you would expect from a TLS implementation, and not the 17 states that we've seen before, and where you can actually find indications of various serious vulnerabilities that were discovered over the years. So then to conclude, so I hope by now I convinced you that the state machine inference is actually quite a useful technique and can be used to find some well, serious security issues, but also some other interesting bugs. And this research also showed that everybody interprets their specifications differently, so it would actually help to include an explicit state machine or a figure of a state machine in these specifications, so at least people know what they should be implementing. And if you're interested in playing around with this tool to learn some protocols yourself, then you can find my code on GitHub. And then I would like to thank you for your attention and take any questions that you might have.